In this video, we're talking about confidence intervals, one population, mean, normal with Rguroo. Suppose your company makes iPhone cases and you want to ensure their quality, specifically the dimensions. How can you check the average width, let's say, of all the cases you make so that you know they'll fit properly? Theoretically, you could measure every single case, but that is definitely not a feasible thing to do. There are too many cases to measure and it would cost too much money cut into your profits to make that happen. So instead, you can take a sample of your iPhone cases and measure the width of each case and then take the sample mean and use that as your estimate of the population mean, right? But is that the best estimate? And also, depending on the sample you take, your estimates can be wildly different from one another. For instance, I could take a sample of iPhone cases from the population, and you could take a sample of iPhone cases from the population, and we can both figure out the sample mean width for each of our samples, and they could be completely different. So who's more right? Who's closer to the true estimate of the population mean width based on our sample? So we've got to figure out a better way. And one way to do that is using that sample mean that we found in a calculation to not find the exact population mean, but to at least narrow it down into an interval called a confidence interval. So we start off with a point estimate, which again is your sample mean, and then we use that to calculate an interval that estimates the mean instead. And so you might think, well, why do I want to estimate an interval? Well, it's sometimes really hard to estimate a true mean, especially if you've got a very large population. So instead of saying the population mean is this exact number, we're going to say the population mean, we're not exactly sure the exact population mean, but we can tell you with confidence that it falls between two specific numbers. So in this section, in this video, we're specifically going to be talking about finding a confidence interval to estimate a population mean. And in later sections, we're also going to talk about finding confidence intervals that estimate a population proportion. This particular section that we're covering is going to give a lot of the basics of confidence intervals that will apply to when we find confidence intervals that estimate means as well as proportions. So I'm going to go ahead and start talking about proportion confidence intervals alongside mean confidence intervals as we start. But all of the examples in this section will deal with confidence intervals for population mean. And I'm just going to start the conversation about the proportions since these basics will apply to both. All right, so just to remind you guys some vocabulary words that you learned earlier. Parameter. Parameter is a number that estimates the population. So a type of parameter would be the population mean. Recall this notation for population mean. That is a parameter. And that is what we're estimating here. We're trying to figure out what is the population mean. Now, population mean is not the only kind of parameter. Again, a parameter is a number that estimates something about the population. So we also have population proportion. That's another parameter that we can estimate using confidence intervals. That notation is just a capital P. Now, to estimate one of these parameters, you've got to have something that you start off with, and that is the point estimate I had mentioned on the previous screen. And the point estimate is a single number that estimates a parameter. If you're estimating a mean, you would start off by using the point estimate of a sample mean. And if you will recall, the notation for sample mean is x bar. Hopefully you have not forgotten, but if not, we are reminding you. And so since we're also talking about, I forgot to write population mean up here. And since we're also talking about the other parameter, population proportion, I might as well go ahead and write that down as well for you. Population proportion. As a point estimate, you would start off with a sample proportion. That is considered a point estimate as well. And that notation is P with a caret top. That is read P hat. So X with the line on top is called X bar. And P with the caret on top is P hat. X bar is sample mean. P hat is sample proportion. Both are point estimates that are single numbers that estimate a parameter. So a sample mean would estimate a population mean, and a sample proportion could be used to estimate a population proportion. And again, we said how, okay, it's a good start, but it's not good enough. So instead, we want to use that to estimate the proportion by estimating it into a range of numbers called a confidence interval. So a confidence interval is a range of numbers that gives a lower boundary and an upper boundary of what a parameter is likely to be. So if you look at these two sentences below, these are, the first one is just estimating the parameter with the point estimate or the sample mean. So in other words, we could say, I think that the average width of our iPhone cases is 67 millimeters. Or I think the population mean, that's what average is mean. And specifically, we're talking about the population mean. So I think the population mean width of our iPhone cases is 67 millimeters. And that 67 would have been, let's say, the sample mean that we got from our sample. And it's an estimate, but is this the best estimate? It just depends on what the sample is, and how close that sample mean really is to the population mean, right? So rather than doing that, we're going to say something like this, and this is going to give it in terms of a confidence interval. I am 95% confident that the average width of our iPhone cases is between 66.8 and 67.2. So instead of pinpointing your population parameter, in this case population mean, down to being one number, which is hard to do, we say, well, we don't know the exact number that our population mean width would be, but we can say it's somewhere between these two numbers here, somewhere between 66.8 and 67.2. It's somewhere within that boundary. So I don't know the exact number, but I know it's somewhere between these two numbers. Notice, not only did we give an interval, we also gave a percentage of confidence. This is called a confidence level. And confidence levels, they tell how confident we are that the true population parameter will fall within those boundaries of our confidence interval, how confident we are. And basically it means, in this case, if we were to repeat the process we used to calculate this confidence interval of 66.8 and 67.2 being the boundaries for the true population mean, 95% of the time, if we repeated this process a large number of times, 95% of the time, the true mean would fall within those boundaries. And that means 5% of the time, it would fall outside of what we estimated. But 95% of the time, we would be correct. That's what that means. So you can have any confidence level you want to use, but I will say, you don't want to give a confidence level like, I'm 60% confident that the average width of our iPhone cases is between 66.8 and 67.2, because what that would mean is that if you were to repeat the process of calculating the confidence interval over and over and over again, you would only be correct 60% of the time. 60% of the time, the true population mean would fall within the interval, and 40% of the time, it wouldn't. So you can see where that confidence level of 60% is probably not the best to go with. So typically, we see confidence intervals that are 90% and higher. We're going to talk more about that confidence level later. So other things, I just mentioned the confidence level. So there is a confidence level. You can't just have a confidence interval. There is always a confidence level that goes with it. And the person that is calculating the confidence interval, that's making the confidence interval, typically decides what the confidence level is going to be. And it's usually, like I said, above 90%. Now, the confidence interval, how do we find that lower boundary and the upper boundary for that range? I can tell you that those boundaries are symmetric about the point estimate. So let's show you here. All right, so let's say this line here represents the confidence interval of the mean width of the iPhone cases, which was between 66.8 and 67.2. So we are 95% confident that the true mean falls somewhere between those two numbers. So those two numbers, they are a range, but they are symmetric about the point estimate. And the point estimate was the sample mean, which was, let's see, we said it was 67. So what that means when we say it is symmetric, let me use a different thing there for that. It's symmetric about the point estimate. So in this case, the sample mean. It means that the distance between the sample mean and the upper boundary is the same as the distance between the sample mean and the lower boundary. The distances are the same. Now that distance is called a margin of error. So I'm going to write margin of error here. So the distance between 66.8 and 67 is the margin of error. Margin of error here as well. That is actually the number 0.2. That's how far it is. So between 67 and 67.2 is 0.2. And between 66.8 and 67.2, I'm sorry, between 66.8 and 67 is also 0.2. 0.2 is what we call a margin of error, and it is the distance from the point estimate to the edges of the confidence interval. So in this case, the margin of error is 0.2. And this interval can be written as 67 plus or minus 0.02. And what that means is the 67 is in the center, and if I subtract 0.02, I get the lower boundary of 66.8, and then if I add 0.02, I get the upper boundary of 67.2. So that's how that works. So we start off with the point estimate, which is your sample mean, or in future we'll be doing sample proportion, and then we will calculate our margin of error. Now your margin of error is going to be related to your confidence level. So once you figure out what that margin of error is, you add it and subtract it to the point estimate, and that will give you your lower and upper boundary, and then you will have your confidence interval. So As I said, you can do confidence intervals for means to estimate a population mean. You can also do a confidence interval to estimate a population proportion. Today, we're going to be talking about confidence intervals to estimate a population mean. Now, depending on how the problem is set up will determine kind of your path. So if we have certain assumptions that are true, we will use one procedure. And if other assumptions are true, we will use another procedure. Let's look at these bullet points here. So if we know that we are estimating the confidence interval for a mean, and if they give us the population standard deviation, which, if you will recall, is denoted by this notation here, sigma. I'm going to write it out just in case you've forgotten. That is population standard deviation, right? If that is given, if that is known, if the population standard deviation is known, and either the population is normally distributed or the sample size is bigger than 30, you are going to use the procedure that you're learning in this video. So, again, one of the two of these have to be true. Either the population mean is normal or the sample size is larger than 30. It's one or the other. And if the population standard deviation is known, we're going to use a process that I call Z interval. Basically, I have a formula for it that I'm going to show you today. I'm also going to show you how to do it with Rguroo. And you are going to use this procedure again if two things are true. The first thing that has to be true, it could be one of two things. It's either the population is normally distributed or the sample size is bigger than 30. The second thing that has to be true is that we have to know the population standard deviation. And if one of the first two things is true and that last thing is true, then again we will use the formula for the Z interval, or we will go into Rguroo and find a Z interval. Now, recall, why does it matter whether it's normally distributed or the sample size is bigger than 30? This has to do with central limit theorem. And so if you'll recall, central limit theorem we learned previously basically says that no matter what the distribution looks like, whether it's symmetric, so a normal distribution or not, if you take a large sample of bigger than 30, and if you were to take a lot of samples from the population and each of those samples were bigger than 30, and you were to line up all of the sample means into a histogram, it would create a normal distribution. So whether or not the population has a normal distribution, the sample means will make a normal distribution. And so with that, I just want you to recall that the mean of the sampling distribution is the same as the population mean, and the standard deviation of the sample means, which is called standard error, if you recall, is the standard deviation over the square root of n. So we just want to recall that because standard error is going to be part of our formula. And we just want to remember that when we're using the central limit theorem, that our standard deviation is actually the standard error. The standard deviation of the sample means is the standard error, the standard deviation over the square root of n. Okay, so let's talk about confidence levels real quick. So when we find a confidence interval, it basically means that we're finding all the values for the population mean that would not make our sample unusual. So what would be the usual samples and what would be considered unusual samples. Uh, so if you recall this normal curve here, the area underneath represents proportion. It also represents probability. And a probability that is less than 0.05 up to this point is what we have always considered unusual. So take, for instance, this normal curve with 95% shaded in. We can say that 95% of the data are within 2 standard deviations of the mean. We could also say that the probability that you would choose at random a number that falls within 2 standard deviations of the mean is 95%. How does that relate to it being unusual? All right, well, here's the thing. What's on either side of these? So if 100% is the whole thing, 95 is the middle, each side would be 2.5%. 2.5%. Both of those percentages, again, represents probabilities. The probability that it is more than 2 standard deviations is 2.5%. The probability that it's less than 2 standard deviations is 2.5%. If you had a number that falls above 2 standard deviations, that has a low probability of occurring. That would be considered unusual. Anything up here is unusual. Anything down here is unusual. Because those numbers are less than 5%. Now, what we have to do is we aren't necessarily going to keep 5% as what we consider unusual. We can redefine that. But the point is that we are going to take our confidence level and we're going to figure out basically the number of standard deviations away from the mean each of the boundaries for that center confidence level percentage is. And anything outside of that is what we're going to consider unusual. And it might sound a little complex, but I think that as we talk about it, it will get a little bit easier to understand. So if you get a sample mean of 23, you know that the sampling distribution has, and you know that the sampling distribution has a standard deviation of 1.5. Okay, so we're just saying hypothetically, if you already knew this, based off of things that gave you the problem, you knew that the sample mean was 23, and then you took and you found the standard deviation and divided by the square root of n, and you got 1.5. That's the standard deviation of the sample means, also called the standard error. Right? Okay. And if they want us to find the 95% confidence interval for population mean. So what we do is we start off with our point estimate, which is the sample mean. We start off with that. Our point estimate. In this case, which is X bar. And then we are going to add and subtract the margin of error. So how do we find the margin of error? So what we're going to do is you find the standard deviation, which in this case is the standard error because you're having to use the central limit theorem because we're dealing with a sampling distribution, the distribution of the sample means. And so what we're saying is the standard deviation of the sample means is 1.5. So how far out do you go for 95% of the data? So if you'll recall, 95% of the data, according to empirical rule, is to go out 2. standard deviations each way. So if I go out 2, if I go out 1, I'm adding 1.5. If I go out 2, I'm adding 1.5 again. So I'm going up 3, and then I'm going down 3. So I'm going up 1.5 twice, which is again 3, and 1.5 twice I'm going down, which is also 3. So the margin of error in this case is 3. So 23 minus 3 would be 20, and 23 plus 3 would be 26. So we would say that we are 95% confident that the true mean falls between 20 and 26. So notice that I have two notations here for that. I've got the 23 plus or minus 3. That's one way to write the confidence interval. The other way to write it is to write it in parentheses with the lower and the upper boundary separated by a comma. You could also write it like this. 20 is less than or equal to the population mean, which is less than or equal to 26. That means the same thing. That's another notation for it. And then you can also write it in sentence form, which we're going to do a lot. That's called interpreting the confidence interval, is writing it in sentence form. But we'll talk about the sentence form structure later. Typically, I write it like this a lot, and I think you'll see a lot of the homework will have you put it in this way as well, in parentheses with a comma in the middle. All right, so let's talk about finding the pieces of this for finding the confidence interval. So again, if you recall what we did, we started off, we found the sample mean, or they found it for us. And then we found the standard error, which is the standard deviation divided by the square root of n, which would be the standard deviation of the sample means. We figured that out. And then based off our confidence level, we figure out how many standard deviations each way you need to go out from that sample mean. So again, with the 95%, we know 95% is 2 standard deviations above and below the mean. So we went up 2 standard deviations, and we went down 2 standard deviations, and we got our confidence interval. Now, we knew 95% is 2 standard deviations each way, but what if you were, let's say, 90% confident? How many standard deviations is that each way? How many is 99%? How many standard deviations is that each way? So we have to come up with a way to figure out the number of standard deviations each way that you're going to go so that you can calculate this. So let's go through the steps for finding the confidence interval. There is basically 3 pieces. All right. You're going to start off with your point estimate. In this case, it's the sample mean. And then you're going to calculate, again, the standard error. So the standard error is the standard deviation divided by the square root of n. Because the standard error is our standard deviation of the sample means, right? And so this is something that we've done, but you've not seen this notation before. We're going to find the z value that corresponds to the confidence level. And what that means is we're going to figure out if you've got the confidence level percentage here, you're going to figure out how many standard deviations, in this case standard errors, above and below the mean are the boundaries. And this is something we've done in a previous chapter. So if we know the middle percentage, can you find the lower and the upper boundary? Now, notice it says we're finding z-scores. So if you recall, a z-score is the number of standard deviations away from the mean that a number is. And so z-scores to the left of the mean have negative values. Z-scores to the right of the mean have positive values. But basically what I'm telling you here is if you find the z-scores for, let's say, the center 95%, the z-scores for those, for the center 95%, is -2 and +2, because it's telling you how many standard deviations above the mean it is going up 2 standard deviations, and then how many standard deviations below the mean, it's going down 2 standard deviations, so that would be -2. So how many standard deviations above and below the mean are the boundaries for the confidence level percentage? And so you are going to find the z-values that correspond with that, because those z-values are actually the number of standard deviations it would be, because that's what z-values measure. So for this particular thing, we are going to use the standard normal curve. And remember, for the standard normal curve, the mean equals 0 and the standard deviation equals 1. So for this particular calculation, we're going to calculate how many standard deviations above and below the mean the boundaries for the middle confidence level percentage would be. And that again will tell us how many standard deviations above and below the mean those boundaries are. And that is what is called a critical value. We call it a critical value, and then we use this fun notation here, z alpha over 2. So z alpha over 2, so again, this little notation here, that is alpha. It is lowercase in case anyone is interested. So z alpha over 2 is just a notation. The whole thing is just a notation. It's not a formula. It's just a notation. So don't try to do any crazy stuff with it, like figure out what alpha is divided by 2. Just look at it as a notation. And again, this is called a critical value. It is the number of standard deviations above and below the mean, the boundaries, I ran out of space there. Let me just rewrite boundaries as one word on the next line here. The boundaries of the confidence level percentage are. Right? And so if you know how many standard deviations that is, you can then multiply the number of standard deviations you just found times the standard deviation, in this case the standard error, and that's going to basically give you the distance between the sample mean and the boundaries. That's going to give you the margin of error. So the margin of error is found by multiplying the critical value, which is z alpha over 2, times the standard error. And then, if you will recall, the standard error is sigma, which is the population standard deviation, divided by the square root of n. So to find a confidence interval, you start off with a point estimate, and you add and subtract the margin of error. And the margin of error is found by finding the critical value, which again, we start with our confidence level, and we find the number of standard deviations from the mean, from the center, is the boundaries, which will give you a z-score, which again is the critical value, z alpha over 2, and you multiply that times the number of standard deviations. Because again, this is telling you how many standard deviations above and below the mean we're considering usual, and you multiply that times what we're saying our standard deviation is, and that's going to give you the boundaries of the confidence interval. So again, start off with your point estimate, in this case x bar, add and subtract the margin of error, which is the critical value times the standard error, and that's the formula. So this formula here that we see, this formula is the formula that you are going to use when the assumptions, one, either the population is a normal distribution or the sample size is bigger than 30, and two, we know the population standard deviation, which you kind of need to know it because that's in the formula here. All right, so let's talk about the critical value, the Z alpha over 2. Now, this is something that you guys, we've done before. We just didn't look at it as a critical value. So what we're saying here is we're saying that our confidence level is 90%, that we are 90%, we want to be 90% confident that our confidence interval, that our true mean will fall within our confidence interval. That's what we want to say here with this. So what we're saying is we're considering this center 90%. We're considering that usual, and anything that falls outside of that would be unusual. And so what we're going to do now is we're going to estimate how far from the mean these boundaries are, and that's going to tell us how many standard deviations to go out above and below the mean for our confidence level. Our confidence interval when we find it. Now, again, because we're trying to figure out how many standard deviations we need to measure this in z-score, so we're going to use the standard normal curve. So in this case, the mean is 0 and the standard deviation is 1. And just real quick, I just want to fill in all of the percentages for this particular curve. We've got 90% in the middle. If the whole thing is 90%, the whole thing is 100%, we got 90 in the middle. That leaves 10% left over, and you got to divvy that up between the two sides evenly. So we've got 5% on the left and 5% on the right. So our lower tail is 5% and our upper tail is 5%. So we're going to go to our guru. And I'm just going to review the steps for our guru. We're going to click on probability simulation tab. And then the probability drop down, we're going to choose probability calculator. And then when we choose probability calculator, you're going to choose continuous. And we are given the probability. So we're going to choose probability to values. It should stay, the distribution should stay normal. You're going to put in the mean, which will be 0. You'll put in the standard deviation, which will be 1. And you're going to choose between. And then it's going to ask for a lower tail, which will be 0.05, and then an upper tail, which will also be 0.05. Okay? So again, our guru, probability simulation, in the probability drop down, choose probability calculator, choose continuous. This is really quick. It looks like a lot of steps, but it's really quick. Make sure it says probability to values, not values to probability. And then distribution should stay normal, which is the default. Put in 0 for your mean, 1 for your standard deviation. We're going between, and then you need to give the lower tail and the upper tail. So let's look at that with our guru. So go to probability simulation, click on probability drop down, choose the probability calculator. When you do, it'll give you the choice of continuous and discrete. This is continuous. A box will pop up. We want to make sure that we choose probability to values, normal distribution. The mean is 0, standard deviation was 1. Those are the defaults. And we want to change this here to, actually, I said between, but it should say between tails. And then it'll ask for a lower tail and an upper tail. So the lower tail we said was 0.05. And the upper tail is 0.05. I'm going to go ahead and graph so you can see the graph as well. And so if you look at this center here that's shaded, that is 90% of the data, right? And so what we're saying is these two boundaries here, that the boundary for the upper boundary for this 90% is 1.6. This is actually if you look up here, you can see the actual number 1.645. 1.645 standard deviations above the mean and 1.645 standard deviations below the mean for the lower boundary. So this is actually the rounding here, 1.64. It should be 1.645. So that would be your critical value here. That would be your critical value. So let's write this down. What we just found was our critical value. So our Z alpha over 2 is equal to 1.645. Now we had 1.645, and that's what we're finding here. This was 1.645 there, and this is negative 1.645. I would say for critical values, I usually go out 3 decimals. So that would be my suggestion for you, is make sure you go out 3. So look for, I know that at the bottom of the graph it went out 2. Look at the top for 3 decimal places for that. So what we found again is the number of standard deviations above and below the mean. The boundaries for 90% are. All right, so let's do this again. And this is just a screenshot of what we just did. I'm just going to highlight here the numbers. So one was positive, one was negative. Which one do you use? So again, they're just showing you the number of standard deviations above and below the mean that those boundaries are. So whether it's positive or negative, it's still 1.645 standard deviation. So always just go with the positive because it's a distance. Let's do 98%. All right, so if we've got 98% in the center here, what's left over? So the whole thing is 100%. That leaves 2%. So that's 1% on either side. So we're going to go to Rguroo. We are going to go to probability and simulation. In the probability drop down, we're going to choose probability calculator. And we're going to choose continuous. And then in the box, we're going to choose probability to values. It should say a normal distribution. The mean should be 0. Standard deviation, again, 1. And we're going to go between tails. And then for the lower tail, we're going to put 1%, which we will put in as a decimal, 0.01. And for the upper tail, we're going to get 0.01 as well. So let's switch screens. I'm just going to go back to basics. And I'm going to switch the tails because everything else is the same. And it looks like we get, it says 2.33 here, but again, I want to go out 3 decimal places, so I'm looking up here, 2.326, negative and positive. So again, these boundaries are 2.326 standard deviations above and below the mean. So that means our critical value is 2.326 standard deviations above and below the mean. So I'm just going to fill this in here and here. So again, this is the number of standard deviations. It's not the margin of error. So the margin of error is going out the standard deviations that number of times. So I would need to figure out what the standard deviation is and go up 2.326 of those standard deviations each way. That's where that multiplication comes in the formula. So let's do one. Let's do cereal box weight, example 5. A machine fills cereal boxes that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It is known from past experience that fill weights are normally distributed with a standard deviation of 0.2 ounces. Construct a 92% confidence interval for the mean fill weight. So a couple of things. We're estimating a confidence interval for a mean, so we need to check our assumptions. So the first is either it has to be a normal distribution or the sample size is bigger than 30. Well, the sample size is 6 boxes. That's not bigger than 30. But it does say that from past experience, it's known that the fill weights are normally distributed, so we can check that assumption. The second assumption is that we know the population standard deviation. So let's go through this again and find where do they talk about the standard deviation. So they mention it here, standard deviation is 0.2 ounces. Now here's the deal. There are two types of standard deviations. There's a population standard deviation, but there's also a sample standard deviation. So which one is this? Is this a population standard deviation or a sample standard deviation? Well, let's read the sentence. It's known from past experience that fill weights are normally distributed with a standard deviation of 0.2 ounces. It doesn't say. It doesn't say population standard deviation, and it doesn't say sample standard deviation. So that leads us to use our context clues. So here's the deal. It says it's known from when? It's known from past experience that fill weights are normally distributed with a standard deviation of 0.2. So what we can say is this is from the past. It's not from this sample of 6 boxes. So in order to be a sample standard deviation, it would have to apply to this sample of 6 boxes. And this is applying to the past. So we're going to say that this here is a population standard deviation. So yes, it is a normal distribution. Since the sample size is not big enough, it is normally distributed, and we know the population standard deviation. So because of that, it is called a z-interval, and we could use this formula where we take the point estimate, which is x bar, and we add the margin of error, which again is your critical value, times the standard error, which is the standard deviation over the square root of n. So that's our formula, and that's what we're going to be using for this problem here. Now, let's label the things that we know and we don't know. We need x bar. We need a z alpha over 2. We need sigma. And we need n. Those are the things we need. Now, we already know that sigma is 0.2. So go ahead and fill that in. What else do we know? Let's just go back through. A machine fills cereal boxes is supposed to put 20 ounces of cereal in each box. So that's a number, but it's not necessarily needed here. A simple random sample of 6 boxes. So that's our n. Our n is 6. Is found to contain a sample mean, that's our x bar, of 20.25. It is known from past experience that fill weights are normally distributed with a standard deviation of 0.2. We've already filled that in. Constructed 92% confidence interval for the mean fill weight. So that's the part we don't know. We know our confidence level is 92%, but we don't know our critical value, our z. So that's where we have to go back and do what we did up here to figure out that critical value first. So I'm going to go here real quick. I'm going to draw this out, and I'm going to fill in. If 92% is in the middle, 8% is left over, so that leaves 4% on either side, right? So I need to find the boundaries of that using the standard normal curve, which would tell me the number of standard deviations each way I need to go. So I'm going to go back here to our guru, and we would go to probability simulation, click here, do the probability calculator, click on continuous. This box pops up. We're going to do probability to values. Mean is 0, standard deviation is 1, distribution is normal between tails. But our lower tail would be 0.04 and our upper tail would be, 0.04 as well. You can hit graph if you want. Let me just show you, if you don't hit graph, it'll just put your data values here. And I said round 2. 3 decimal places for these. So this would be 1.751. 1.751. If you want to see the graph, you can do that. But again, I like to go out to 3 decimal places for these. Okay, so I'm going to fill this in. This is 1.751. So that is the number of standard deviations above and below the mean that the confidence level boundary is what we consider usual is going to be. Anything outside of that, we're going to consider unusual. So we're going to start off with our X bar. Oops. Which is our point estimate, and we're going to add our margin of error, which again is our Z alpha over 2 times our standard error, which is sigma over square root of n. So we're just going to fill in the pieces here. So we're going to fill in the mean, which is 20.25, plus or minus Z alpha over 2, which is 1.751, times the standard error, which is 0.2 over the square root of 6. Now, if you do this part here, 1.751 times 0.2 divided by square root of 6, that's going to give you the margin of error. And then you can add and subtract that number from 20.25. I'm just going to show you. Let me click on a calculator here. Just kind of the way I approach it. Now, if they ask me what the margin of error is, I would do 1.751 times, what was this standard deviation, 0.2. Divided by the square root of 6, and you get 0.1429, blah, 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 blah. But then, if they ask for the margin of error, I'm definitely going to give that. But if they ask for the confidence interval, I'm not going to do this separately. I'm just going to go ahead and do the whole thing. And the reason is because you have to round the margin of error to add it and subtract it. And I like to avoid extra rounding if I can. So what I would actually do is I would start off with this whole formula, 20.25. And I'm going to do this twice. 20.25. The first time I'm going to do it with a subtraction. So I'm going to subtract the margin of error. The margin of error is 1.751 times, I forgot my point there, 1.751 times, I believe it was 0.2 divided by the square root of 6. Let me just double check. Yes, it is. And then if you'll look here, we got 20.107. They don't tell us what to round to. So I'm just going to go out 3. And then the upper boundary, we're going to do the same thing. What you could do is you could just go up here and delete the minus sign and change it to a plus sign. And you get 20.393 if you round. All right, so there we have it. There's our confidence interval right there. We are saying that the true mean serial weight is somewhere between 20.107 and 20.393. We can say this with 92% confidence. So here we're going to interpret. And basically what it means is it means putting it in a sentence. All right, so I'm going to basically give you a little template here. So you're going to say, we or I like to say we because we just did this together, right? We are blank % confident that the true in this case we were estimating the true mean, and you need to put it in context. is between blank and blank. So there's your template. You write a sentence. This is we are, and then you are going to put, let's see if I can do this. So under this is the confidence level. The confidence level percentage that the true parameter in context is between the lower boundary and the upper boundary. And that's what you're going to fill in. So in this case, we are saying we are 92% confident that the true population mean, and then in context, it would be serial weight, is between 20.107 ounces and 20.393 ounces. So you also want to make sure that you give units. So the sentence is basically the same for every confidence interval. The things you want to change are your confidence level, the parameter in context that is being estimated, and then the lower and the upper boundaries. But other than that, I would just keep the sentence pretty much the same. And again, that confidence level, what it means is that if you were to repeat this a large number of times, you would be correct. You would correctly estimate the true mean 92% of the time. 8% of the time you'd be wrong. But 92% of the time, the true mean would fall within the confidence interval that you found based off of this process. All right. And let's do another one. Now, yes, we've only done this with a formula. I promise I will show you another way to do it with technology, but I want to do several with the formula first. So a college admission officer takes a simple random sample of 100 entering freshmen and computes their mean mathematics SAT scores to be 458. Assume the population standard deviation is sigma equals 116. Construct a 99% confidence interval for the population mean score. So are our assumptions true? So two assumptions. One, either it's the normal distribution or the sample size is bigger than 30. Check. The other thing is that we know the population standard deviation. We do, and this one's nice because they actually say population standard deviation, and they give you the notation for that as well. Sigma is 116. So both of our assumptions work out, and that means, those assumptions mean we can use this particular formula for a Z interval. All right, so let's fill in what we know. X bar is the sample mean, and that is 458. And then I'm going to skip the Z alpha over 2 for now. I'm going to go to sigma. Our sigma population standard deviation is 116. N is our sample size. That's 100. All right, this one is the only one we don't know. So I'm going to go down here to find it using the standard normal curve, putting the confidence level in the middle, 99%. If 99% is in the middle, what's left? So what's left is 1%. And if I split that between the two sides, that gives me 0.5%. 0.5%. Now, 0.5% is crazy. 0.5% is the same as 0.005. So my lower and my upper tail is going to be 0.005. So I'm going to go back up here. Since I've got this calculator up already, I'm just going to change the tails to 0.005 on either side. All right, and it looks like we get 2.58 standard deviations. It looks like it's 2.576 if we go to 3 decimal places rather. All right. So now that we know that, we know everything we need for the formula. So again, the formula is x bar plus or minus z alpha over 2 times sigma over the square root of n, and I don't know why I wrote 2 here. Sorry about that. You're probably wondering, what was she writing there? Okay, so fill it in. Fill in what we know. So it's 458 plus or minus 2.576 times 116 over the square root of 100. And again, if you need to find the margin of error, let's start here. The standard error is this, 116 divided by square root of 100. If you need to find the margin of error, it's the 2.576 times the 116 over square root of 100. If they ask for the point estimate, it's here. So if they ask you for each piece, you can give them. But we can go straight to the calculator. And we can just do this twice. We can do this. I always do the minus first. So 458 minus the 2.576 times the standard deviation, which is 116, divided by the square root of 100. And it looks like we get 428.118. So I'm going to write that down. 428.118. And we're going to do this again with a subtraction sign. So I'm just going to go here. I'm going to click on the minus sign. I mean, you can retype it if you want, but I just like to change to a plus sign. We get 487.8816, which is 882. All right, so what we're saying is that we're not sure what the mean SAT score is, but we can say with 99% confident that that SAT score falls between 428.118 and 487.882. So let's interpret with a sentence. We are blank percent confident that the true, and then the parameter we're estimating in context is between blank and blank, period. And we fill those in. We are 99% confident that the true, we were doing a population mean, and you have to give it in context. Mean of what? Mean SAT score. And actually, we could actually say mean math SAT score, because that's what we're doing. A college admissions officer takes a simple random sample of 100 entering freshmen and computes the mean mathematics SAT score. So we are 99% confident that the true population mean math SAT score is between 428.118 and 487.882. And because it's a score on a test, there's no units we need to add there. So there is our sentence. Yay! All right, let's do another one. Baby weight. According to the National Health Statistics reports, a sample of 360 one-year-old baby boys in the U.S. had a mean weight of 25.5 pounds. Assuming the population standard deviation is sigma equals 5.3, construct a 94% confidence interval. So our assumptions are good. 360 is bigger than 30, and we know the population standard deviation is 5.3. So we can use our x bar plus or minus z alpha over 2 times sigma over square root n. So let's fill in what we know. X bar is our sample mean. The sample mean weight was 25.5. And our sigma is 5.3. Our N, our sample size is 360. And we still have to find our Z alpha over 2. So come over here, draw our curve. Our confidence level is 94%. If 94 is in the middle, that leaves 6% left over. And if you divide that in half, that's 3% on either side. So quickly going here, changing it to 0.03 and 0.03. 1.881. All right. So, let's go ahead and use the formula. So we have 25.5 plus and minus 1.881 times 5.3 over the square root of 360. And we're just going to put those in the calculator. So we get 25.5, and I always start off with the minus first, minus 1.881 times 5.3 divided by the square root of 360, and we get 24.97, if it rounded 3 decimal places, 975. And the upper boundary, I'm just going to go back and change that minus sign to a plus, and I get 26.025. So writing our sentence, we would say we are 94% confident that the true mean or true population mean, and then again you have to put it in context. So what were we estimating? We were estimating the mean weight of 1-year-old baby boys. So the true population mean weight of 1-year-old baby boys is between, and this one we will need to give units, 24.975 pounds and 26.025 pounds. Again, you're filling in your confidence level, your parameter in context, and then your lower and upper boundary with units filled in. All right, so let's look at example 8. In a simple random sample of 100 electronic components produced by a certain method, the mean lifetime was 125 hours. Assume the component lifetimes are normally distributed with population standard deviations of 20 hours. Construct a 90, a 95, and a 98% confidence interval. So we're going to actually do this 3 times. So I'm going to add a page here to give me extra room. All right, so I'm going to do this 3 times. All right, so the first time I'm going to do this, I'm going to do a 90% confidence level, and then I'm going to do a 95% confidence level, and then I'm going to do a 98% confidence level. So for each of these, the sample mean is 125. The standard deviation is 20, and the sample size is 100. So sample mean is 125, standard deviation is 20, sample size is 100. The sample size is big enough, and they do give us a population standard deviation, so we can use our x bar plus or minus z alpha over 2 times sigma over square root of n as our formula. All right, so what is going to change here is our z alpha over 2. So let's figure out for each of these what our z alpha over 2 would be. So if 90 is in the middle, that leaves 10% left over, so that's 5% on either side. So going to our guru, we're doing 5% on either side, and that's the 1.645. All right, so I wrote that down. So let's do another one. If 95% is in the middle. Now, oops, if 95% is in the middle, that would be 5% left over, so that would be 2.5% or 0.025 on either side. So if we did this, we're going to put in 0.025 on each side, and we get 1.960, which is approximately 2, which lines up with empirical rule. Right? Because if you recall, 95% of the data is within 2 standard deviations of the mean. So it's approximately 2 standard deviations, and we get that approximation from 1.960 standard deviations above and below the mean. One more, let's do 98%. If 98 is in the middle, that leaves 2% over, so we have 1% or 0.01 on either side. So going back to this, our lower tail is 0.01, our upper tail is 0.01, and we get 2.326. Okay, so now we have everything that we need. X bar is 125, sigma is 20, n is 100, and then the z alpha over 2, the critical value, varies. So we're just going to fill out each one real quick and see how they differ between the different confidence levels. How does it change the confidence interval? So again, we have x bar plus or minus z alpha over 2 times sigma over square root n. All right, so that would be 125 plus or minus. The critical value for 90% is 1.645 times the standard deviation, which is 20 over the square root of 100. So let's go to our calculator. And we have 125 minus 1.645 times 20 over the square root of 100. And we get 121.71. So let's write that down. 121.71. And we'll do this again with a plus sign. And you get 128.29. So we would say we are, let's just write this out, we are 90% confident that the true population mean, and in context, this is the mean lifetime of electronic components is between 121.71 hours and 128.29 hours. All right, so there we go. We've got 121.71 to 128.29. All right, so the next one, we still have our x bar plus or minus z alpha over 2 times sigma over square root n. The problem is going to look really similar, except we're changing our critical value to 1.960. And we're just going to go over and do it. So I'm just going to actually do that. And we get 128.0, I'm sorry, 121.08. And do it again with a plus sign, 128.92. And I'm not going to rewrite this sentence, but it would be, we are 95% confident that the true population mean lifetime of electronic components is between 121.08 and 128.92 hours. All right, so let's do one more. So we have 125 plus or minus, the critical value for 98 was 2.326 times 20 over the square root of 100. Just going to change the critical value there, minus 2.326. And we get 120.348. And we do it again with a plus sign, and we get 129.652. So we are 98% confident that the true population mean lifetime of electronic components is between 120.348 hours and 129.652 hours. So how did this compare, right? So let's just do a number line. Let's just look at these. All right, so for each of these, we've got 125 is in the middle. So let's kind of locate these numbers. And I'm just going to do estimates, all right? This is kind of just a sketch. 121.71 would be here, and then 121.08. Let me do a different color. Let me just do it this way. All right, and then the upper boundary for that would be 128.29. So you can see between here and here, this is your 90% confidence interval. Now, where would these other numbers fall? So if you think about 121.08 to 128.92, 121.08 is somewhere to the left of 121.71. And 128.92 0.92. It's somewhere to the right of 128.29. And so that is the confidence interval that's the confidence interval that is 95%. So you can see when we went from a confidence level of 90%, that confidence interval was more narrow than the confidence interval for 95%. So it's definitely a wider estimation. And let's look at what happens when we went down to 98%. It went to 120.348 up to 129.652. So it got even wider. So what that means is as the confidence level increases, the confidence interval also increases. So the more confident you are, the wider your confidence interval is. And the thing is, we're trying to narrow it down. You don't want it really, really wide, right? You're trying to narrow it down. So you kind of have to try to find a balance. Let's look at this here. This should say, okay, so we have 3 illustrations here. And it's showing that as the confidence interval increases, as the confidence level increases, the confidence interval gets wider. But this is nice because it kind of shows you the illustration. So if you look at the first one, this is if we had a 75% confidence level. And so in this case, the margin of error is smaller, but the confidence interval accurately estimates the mean only 75% of the time, right? So it means 25% of the time you were wrong. So I want you to look here at this. So you can see like each of these little lines here, these horizontal lines, they represent where you took a sample and you found the confidence interval. And so we found a lot of them. And so they're going to vary because the sample means are going to vary. And so the true mean is this vertical line here. So if the confidence interval crosses that mean, that means the mean is within that confidence interval and it accurately estimated the mean. If it doesn't cross it, then it did not accurately estimate the mean. So you can see all of these bars that are on the outside of this line, all of those times it incorrectly estimated the mean. So it was only right 75% of the time, but it was wrong 25% of the time. Now, moving up to 95% confidence level, so you can see it crosses this line, the mean line, a lot more times, but the interval is longer. So you can see over here, 75% is really short. It's definitely a longer interval, wider range. But you see fewer lines, like this one here, that don't cross the true mean. So that means that only 5% of the time it is incorrect. 95% of the time it accurately estimates the true mean. The true mean would fall within the interval 95% of the time. And then if you went even further, 99.7, it almost never doesn't cross the line. It almost always crosses the true mean. It almost always estimates it. It's only wrong 0.3%, not even a whole percent. 0.3% of the time it's wrong. The rest of the time it is accurate. But look how much wider these lines are than, say, the 95% confidence interval. So there is definitely a trade-off there. Excuse me. The more confident you are, the wider your estimation is going to get, and we're trying to narrow it down. So you definitely want to find a balance there. So there is a way, though. Let's say that you want a specific confidence level. Let's say you want to be 99.7% confident, but you don't want that super wide confidence interval. You want to narrow it down. So you can have a smaller margin of error, which is what makes the confidence interval so wide. You can have a smaller margin of error if you calculate the sample size you need and you have a sample size big enough. So what would be big enough? So there's a formula for that. So the formula is N, which will be sample size, is equal to the critical value based off of your confidence level times your sigma, which is the population standard deviation, divided by M. So M, guess what? M stands for margin of error. And then once you multiply and divide, you square it. So once you do that, you need to round your answer to an integer because this is a sample size. You can't sample half a person, right? So, and you always have to go up because let's say you had 12.3. That would normally round to 12, but 12 is not big enough to have the small margin of error that you want. So you need to always go up. So you would round that to 13. All right, so let's look at a problem like that. A population standard deviation for the age of students at a college is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of these students, how many randomly selected students must be surveyed? All right, so they didn't ask for a confidence interval. They said how many students must be surveyed in order to have the confidence level with the margin of error that they're giving here. So we're going to use the formula N equals Z alpha over 2 times sigma over margin of error squared. So we need to start off by finding our Z alpha over 2. So we're doing 95% in the center. If 95 is in the center, you got 0.025. So 2.5%, which is 0.025 on either side. And this is the same thing it was earlier, but in case you forgot, we'll put this back in. And I believe we get, 1.960. 1.960. All right. Our sigma was 15. And our margin of error, how do you find that? That is right here. When they talk about within a certain amount of, that would be within a certain amount, that is your margin of error. So the margin of error in this case is 2 years. All right. So here we go. Z alpha over 2 is 1.960 times 15 over 2 squared. The other way you can do this is you can square each of the individual numbers. You can square 1.960, you can square 15, you can square 2, and then do your multiplication and division. I think it's easier to do it first. Do the multiplication and division first, and then square it at the end. All right, so what I would do is I would do Desmos, I would do parentheses 1.960 times 15, and then divided by, and actually, let me do it this way. Excuse me, you guys, I'm sorry I have a cold. Oops. 1.960 times 15 divided by 2. And then I'm actually going to put parentheses around the whole thing like that. So I can square it. So then I'm just going to hit the squared button like that. And that is going to give me 216.09. So actually, let me just show you starting over. What I would do is I would do, if you're using Desmos, that is, I would do 2 parentheses at the beginning and then 1.960 times the 15, which is in the numerator, and close the parentheses for the numerator, divided by 2, and then go and close that parenthesis and then square it. And you get 216.09. Which you have to bump up to the next whole number, which would be 217. So in order to get a 95% confidence interval with a margin of error of 2, you need 217 people in the sample size. All right, so we talked about how to use the formula for calculated confidence interval, formula for sample size. Now we're going to go to Rguroo, and we're going to talk about how you calculate the mean using Rguroo. So if you have a sample size that's bigger than 30, or it's a normal distribution, and you know the population standard deviation, here are the steps. So there's an analytics tab that we've used before. You're going to click on the analytics tab. We used to click on that to get to numerical summaries. So now you're going to click on it and you're going to choose mean inference. And then there's a side menu pops up. It'll say 1 population or 1 and 2 population. You're going to click 1 population. Okay. Once you do that, this box will pop up. Now, if you have data in a data set that you're trying to do a confidence interval for, you can just click on this drop down and choose your data set. But a lot of times we just want to enter some numbers, right? We don't have a data set, but we have a sample mean, we have a standard deviation, etc. So you're going to just fill these in. Sample mean, you put that in. You put in your population standard deviation, and you put in your sample size. If they gave you the sample standard deviation instead of the population standard deviation, you would put that here and leave the population standard deviation blank. Now, just like when we write the sentence out, we have to give context. So you need to give context to your mean by labeling it, the mean of what, and you put that in. And then once you do that, it says confidence level. Now, there's 2 tabs here. Confidence interval test for of hypothesis. We're going to eventually do both. For now, we're leaving it on the confidence interval tab, but you'll put in your confidence level as a decimal, not as a percent. So if it's a 95% confidence level, you put in 0.95. And then because we know the population standard deviation, and because the sample size is either big enough or it's a normal distribution, you're going to choose Z statistic for your method. And then you're going to hit preview. And that's it. So again, analytics, analysis dropdown, choose mean inference 1 population. Fill in your sample mean, the type of standard deviation you're given, sample size, context label for the mean that you're finding, confidence level, Z statistic. Preview. You're done. It's super fast. And then what will happen is it's going to give you a couple little charts here. And so this right here, the lower and the upper CL, that's going to be your confidence interval right there. So, I mean, it gives you other things. It labels the variable. It reminds you your sample size, your mean, your population standard deviation. It actually calculates your standard error and your margin of error. So that would be a way to get those without doing them by hand. You can get them from here. So that's kind of nice, right? And then what we're going to do is we're going to redo examples 6 through 8, but we're going to do them this time using Rguroo. We're just going to make sure that we get the same numbers. So let's just go back up here, starting with example 6. All right, so the things that you need for Rguroo is, and then I'm gonna, I think what I'm gonna do is, no, I'm just gonna leave it. Okay. So what we're gonna do is we need the sample mean, the population standard deviation, and the sample size and the confidence level. That's really all you need. So looking at this is the SAT score one. The sample is of 100 people. Standard deviation of population is 116. Sample mean is 458. Confidence level is 99%. So let's go back here to our guru and get rid of that and minimize that. So the cool thing here is you don't have to figure out your confidence level and all of that fun stuff. You just go straight to the confidence interval. So we're going to go to analytics. In the drop down, you're going to choose mean inference. And you're going to choose one population. We don't have a data set, but we have a sample mean, and the sample mean for example 6 was 458. So you fill that in. And we knew the population standard deviation was 116, and the sample size was 100. And we were doing the mean mathematics SAT score for this one. And then the confidence level was 92%, so 0.92. And we're going to choose the statistic because, again, we know the population standard deviation and the sample size was big enough. Hit preview, and you can see, oh, I'm sorry, let me go back. It wasn't 92%, it was 99%. It was 99%. I misread that. All right, here we go. And so we get 428.12. We got 428.118. So it's the same thing, just rounded. 487.882. If you go back to basics, I would like for there to be a way to graph this. Unfortunately, it does not graph it for us. So all that it's going to show us is this little table. But the point is, it's the same answers as what it was that we got when we worked it out by hand. Let's go to the next one. All right, number 7. This was the mean baby weight. They took sample of 361-year-old baby boys in the U.S. that had a mean weight of 25.5. Population standard deviation was 5.3. Construct a 94% confidence interval. All right, so, oops. I keep saving these and I don't mean to. All right, so go to analysis, analytics, mean inference, one population. Fill in your sample mean. Our sample mean for the baby boy weights was 25.5. And we knew the population standard deviation is 5.3. And the sample size was 360. And we left sample standard deviation blank. This was the mean of the weight of 1-year-old boys, baby boys. And our confidence level was 94%, so 0.94, and we choose the statistic again. And it looks like we get 24.9746, which is the same as 24.975 that we wrote down earlier. And the upper boundary is 26.025, which we also wrote down earlier. So same thing. The next one we did was where we did 3 different ones in one. Let me just go back here so you can see. We did these 3 in 1. So this was the random sample of 100 electric components. The mean lifetime was 125. Standard deviation was 20. And we changed the confidence level. So let's just show you how easy this is. Analytics, analysis, choose mean inference, one population. So I'm just going to delete these out. Okay, so the sample mean was 125, and the population standard deviation was 20. Sample size was 100. No sample standard deviation. Variable label was the lifetime of electronic components. And we're doing a Z statistic because, again, the sample size is big enough and we know the population standard deviation. What's going to change is our confidence level. So we started off with 0.90 and we got between 121.71 and 128.29, which is exactly what we got before. Go back to basics and quickly change this to 0.95. And you can see that we get 121.08 to 128.92, same thing we got earlier. And one more, we did 98%, right? So that was 120.347 and 129.653. Now this one I would say is a little bit the rounding looks a little bit different. So if that's the case, what you could do is you could take this margin of error here and add it and subtract it to 125. So if you're worried about how many decimals you need to go out, right? So what you could do is you could take the margin of error, the 4.6527, add it, subtract it to 125, and get something really close to these numbers, but maybe you're going out further decimal wise. So if, let's say, Newton told you to round to 4 decimal places instead of 3, you could do that by using this mean plus or minus this margin of error. Anyway, so there we go. There we have it. I believe that's all the ones we wanted to rework there. Okay, I want to do one more where they give us the data set rather than individual sample statistics. So it says a random sample of 11 BlackBerry Bold 900 smartphones being sold over the internet in 2010 had the following prices in dollars. And they give us a list. Assume the population standard deviation is 71. Calculate 95% confidence interval for the population mean price. Now the sample size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is technically not big enough. So I'm going to add in here the population is normally distributed. Okay. So technically what you could do is you could find the sample mean, right? And then use that in the formula to calculate the confidence interval to estimate the true population mean price. But we can use Rguroo, and I want to show you how you would do that. All right, so the first thing is first, we need to add this data set. So you're going to go to data, you're going to go to data import, and you're going to choose create data set. And our variable name is BlackBerry. I'm just going to do price. And then I'm going to say this is BlackBerry prices in 2010. Okay. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. All right. So I'm just going to fill these in. Okay, so I've typed in the numbers 230, 484, 379, 300, 239, 350, 300, 395, 230, 410, 460. So I just wanted to double check, make sure I put them in correctly. I'm going to hit Save As. Okay, close that out. All right, so let me show you how to do the confidence interval. So we'll go to Analytics, choose Analysis drop-down, Mean Inference, one population, just like before. The difference this time is we're going to choose our data set, which is BlackBerry prices in 2010. And then you have to choose a variable here, which is BlackBerry price. And notice what happens. It has filled in the sample mean, it filled in the sample standard deviation, and it filled in the sample size. Now, if you will recall the question, they gave us the population standard deviation. They said it was 71. So going back here, I'm going to fill in the population standard deviation is 71. All right. And notice they filled in our BlackBerry price here. And then our confidence level is 95%. So that was my default here. So I'm going to leave that there. And it is a z-statistic since we know the population standard deviation and because I told you that the data was normal. All right, here we go. And it looks like it falls between 301.41, because this is money, $301.41 and $385.32. So let's write that up on this sheet. So it falls between $301.41 and $385.32. So we are 95% confident that the true population mean price of blackberries of BlackBerry Bold 9,000 smartphones in 2010 is between 301.41 and dollars and 385.32. Just real quick, I want to go back to here. So you can see the sample mean is 348.364. You can see the standard error, 21.4073. You can figure out your critical value for 95% be 1.960, and so you could use that in formula and do this mathematically just to double check. You could also do just the sample mean plus or minus the margin of error, which is already calculated for you as well. At any rate, you're going to get these two numbers here for your lower bound and your upper bound, even if you did do it by hand. Anyway, there we go. There we have it. This has been a really long lecture. Hopefully you took some breaks in there. I apologize for my cold. But if you have questions, please let me know. That's all I have. All right.